Hello, my name is Benjamin Lin, and today I will be walking you through the USNCO National Part 1 exam solutions. This will be the first video in a two-part series where I will be going over questions 1 through 30. So without further ado, let's get started. And if you want to follow along with the written annotations, they should be published online at ACS's website around the time of this recording, if not slightly later. So, to start, let's look at question 1. What is the mole fraction of acetic acid in an aqueous solution that is 11.7% by mass acetic acid? So to do a problem like this, where we have a percent by mass, it's always easiest to start with a 100 gram sample. So let's do that. In a 100 gram sample, we will have 11.7 grams of acetic acid. And using subtraction, we can figure out that we will have 88.3 grams of water. We can find the amount of moles of acetic acid in water using the molar masses. So let's just do that. So this would be 60.05 grams per mole. And this would be 18.02 grams per mole. And then I've already ran these calculations before, so I don't need to plug in the calculator again. But this gives you 0.195 moles of acetic acid and 4.90 moles of water. So to figure out the mole fraction of acetic acid, that's just going to be the amount of moles of acetic acid divided by the total amount of moles. So that's going to be 0.195 divided by 0.195 plus 4.90, and that comes out to 0.0382, which is B. Problem 2. Hydrogen peroxide decomposes to give water and oxygen gas. How much 3% by mass aqueous hydrogen peroxide must decompose to afford 4 liters of dry oxygen at standard temperature and pressure? So to do a problem like this, it's always best to start with the balanced equation for what's going on. And we're told it's the decomposition of hydrogen peroxide into water and oxygen gas. So this goes to water plus O2. Let's balance the equation using a coefficient of 2 on the peroxide and 2 on the water, like so. Now, we're given that 4 liters of dry oxygen are produced at standard temperature and pressure. And as some of you might know, at standard temperature and pressure, 1 mole of gas is equivalent to 22.4 liters of volume. So we can use that relationship to figure out how many moles of oxygen are produced. So let's do that. 4.00 liters divided by 22.4 liters per mole, which will give us 0.179 moles of oxygen. And then, using the stoichiometry of this reaction, we can tell that 1 mole of oxygen equates to 2 moles of hydrogen peroxide. So we can calculate the moles of hydrogen peroxide, which comes out to 2 times 0.179, which is 0.357 moles of H2O2. Now, to figure out how much of this 3% by mass hydrogen peroxide solution we'll use, we can set up a proportion. So we know 3 grams out of 100 grams of solution are going to be hydrogen peroxide, and then the amount of hydrogen peroxide we're going to need is going to be this 0.357 moles times the molar mass of hydrogen peroxide. Let's just write the units here so we don't get confused. The molar mass of hydrogen peroxide is 34.02 grams per mole. That's the amount of hydrogen peroxide that we need. And then we're going to divide it by our unknown. We don't know how much of the solution we're going to need. So if my iPad will cooperate, we will find that after solving this equation, X is equal to 405 grams. Oh my God, why is this iPad bugging? 405 grams. And that corresponds to option D. So D is correct. Problem 3. A diamagnetic compound that contains only carbon, hydrogen, nitrogen, and oxygen is 19.99% carbon, 3.35% hydrogen, and 23.31% nitrogen by mass, which is its molecular formula. So, again, we can consider a 100-gram sample. So that's going to be 19.99 grams of carbon, 3.35 grams of hydrogen, 23.31 grams of nitrogen. And then to figure out the amount of grams of oxygen, we know it's going to be 100 minus all of these because that's just going to be the remaining mass in oxygen. So it's going to be 100 minus 19.99 minus 3.35 minus 23.31 grams of oxygen. And to figure out the ratios of these atoms in the molecular formula, we can divide by the molar mass. So carbon, we're going to divide by 12.01. Hydrogen, we're going to divide by 1.008. Nitrogen, we're going to divide by 14.01. And oxygen, we're going to divide by 16.00. So these are our the molar masses of these elements. And then if we do the calculations, this comes out to, I believe, 1.66 moles of carbon, 3.32 moles hydrogen, 1.66 moles nitrogen, and 3.33 moles oxygen. So from these mole amounts, we can see the actual ratio of carbon, hydrogen, nitrogen, and oxygen. And in this case, that is going to be 1 to 2 to 1. Come on, pen. To 1, 2 to 2. And that will give us an empirical formula, not molecular formula, of CH2NO2. All right, so that's going to be the ratio of atoms we're going to expect in our actual answer. So let's look over at our answer choices. So clearly A does not follow this 1 to 2 to 1 to 2 ratio, so that is incorrect. B does exactly follow the 1 to 2 to 1 to 2 ratio, so that's a possibility. C does not follow this ratio, and D does follow this ratio. So how are we going to decide between B and D? Well, looking back at the question, they tell us that the compound is diamagnetic, and a diamagnetic compound repels a magnetic field, but what that tells you about its electrons is that all of the electrons are paired. So now let's just look at like B, for example, right? Carbon is going to have 6 electrons. Each hydrogen is going to have 1 electron, so the total is 2. Nitrogen has 7 electrons, and the 2 oxygens, each of them has 8 electrons, so together they have 16. All right, come on. And clearly, we see when we add all these numbers together, we are going to get an odd number. The number is 22, 24, 31, in fact, 31 electrons, in fact. And if there's an odd number of electrons, that means that not all of them can be paired together. So this cannot be a diamagnetic compound. We can eliminate B. And that leaves us with D as our answer. Problem 4. What is the chloride ion concentration in a solution prepared by mixing 35 mils of 0.35 molar sodium chloride and 65 mils of 0.65 molar calcium chloride? So let's write out the molecular formulas just so we don't get confused. Sodium chloride is NaCl, so NaCl. And calcium chloride is CaCl2. Now, to figure out the total chloride ion concentration, we're going to figure out the total moles of chloride ion divided by the total liters of solution. In this case, it's actually going to be easier to work in millimoles and milliliters, but that's going to give us the same result because both of those units are divided by 1,000. So in effect, it's the same thing. So what we're going to do is figure out the millimoles of chloride ion. So we have 35 mils of 0.35 molar solution, and 65 mils of a 0.65 molar solution. However, this 0.65 molar of calcium chloride solution, what we have to notice is that there's 2 chloride ions for every calcium chloride molecule, so we need to multiply this by 2. And then we're going to divide by the total volume in milliliters, so that we have millimoles over milliliters. And that's going to be 35 plus 65, which is 100. So 100 milliliters. And when we divide this all out, what we end up getting is 0.97 molar. And my pen's not cooperating. Just imagine I boxed that. So D is going to be our correct answer. Problem 5. 17 grams of barium nitrate is mixed with 11.5 grams of an alkali metal sulfate, and the precipitated barium sulfate is collected by filtration, placed in a Tarot crucible, and the crucible heated to drive off water. The mass of barium sulfate obtained is 15.4 grams. Which conclusion is best supported by the data? So the first thing we want to do is figure out what's the maximum amount of barium sulfate we can create with this given amount of barium nitrate. So the way we're going to do that is first find the amount of moles of barium ions. So we have 17, I believe, grams. So we have 17 grams of barium nitrate divided by our 261.32 grams per mole. And that's going to come out to 0.0651 moles of barium 2+. So we can figure out what's the maximum amount of barium sulfate by multiplying by the molar mass. So 0.0651 moles. And then we're going to multiply by, what is the molar mass? 233.37 grams per mole. And what we get is 15.2 grams of barium sulfate. So now looking back at our experimental data, we end up getting 15.4 grams of barium sulfate. And clearly that's not possible with the amount of barium we started with. So something else must be contributing to the amount of mass that we have. And if we look at our options, option C tells us that the barium sulfate was not heated long enough to drive off all the water. And if you can imagine that there's still water in our sample when we mass it, that can clearly increase the amount of mass that we weigh and cause this error. So C is the correct answer. Problem 6. 10 mils of 0.5 molar potassium sulfate and 10 mils of 0.5 molar silver nitrate are mixed, and the mixture is allowed to attain equilibrium. Which ordering of the concentrations of the ions in solution is correct? So to solve this problem, what we can do actually is figure out the millimoles of each of the ions in solution. Because they're all being divided by the same volume, whichever one has more millimoles in the final solution will also have the higher concentration in the final solution. So let's figure that out. So we are adding 10 mils of 0.5 molar potassium sulfate. So let's just write that out. So this is K2SO4. And we're adding 10 mils of 0.5 molar, so that's 5 millimoles of this compound. So we're adding 5 millimoles of this sulfate salt. All right, so you can imagine this would create 10 millimoles of potassium plus and 5 millimoles of SO4 2 minus. Now let's look at the other species. It's silver nitrate, and I believe also 10 mils. So we have, again, this is silver nitrate. Our 10 mils times 0.5 molar is going to give us 5 millimoles. And this is 5 millimoles Ag plus and 5 millimoles NO3 minus. Now, what we have to consider is that when we mix these ions in solution, silver sulfate is actually going to precipitate out. So that is going to precipitate out Ag2SO4. And as silver sulfate precipitates out, that's going to change the amount of millimoles of silver and sulfate in solution. So we would imagine that all 5 millimoles of silver plus will precipitate out. And because we only require half the amount of sulfate, there's still going to be 2.5 millimoles of SO4 2 minus remaining after this precipitation. So we'll have 0 silver plus ions and this amount of sulfate ions, and that gives us our final ordering. So clearly potassium is going to have the most, and then we're going to have our 5 millimoles of nitrate, so that's NO3 minus, which is greater than our 2.5 millimoles of sulfate, SO4 2 minus, and which is greater than our nearly 0 millimoles of silver plus. So let's look at our options, and that corresponds to D. Problem 7. A neutral organic compound is to be separated from a basic impurity by washing a solution of the compound in a hexane with 5% aqueous hydrochloric acid. Which apparatus is best suited for this operation? So first, let's understand the theory of what's going on here. So we have some type of vessel. We don't know what it is yet. We're going to have to decide, like in the answer choices. And we have our organic compound. I'm going to call that O. And we have a basic impurity called B. And this is all in a solution of hexane. So this is hexane solvent. Now our goal is to separate this B out of this organic compound right here. And the way we're going to do that is we're going to pour in some water and aqueous acid, in this case HCl. So we're going to add HCl. And you can imagine HCl is a strong acid. It's going to release its proton, and it's going to protonate the base, which is a proton acceptor. So what we create is Hb+. And Hb+ is a charged species. And we know charged species tend to go in aqueous solution because it can be surrounded by the water molecules and stabilized. So when we mix these solutions together, we're going to have 2 layers because the water and hexane don't mix. We're going to have the water on the bottom and the hexane on top. So hexane and our aqueous layer. And what's going to happen is we're going to have the Hb+ going into the aqueous solution. Come on, please cooperate, pen. And the organic compound, which is neutral, is going to remain in the organic solvent, which is the hexane. So now we have to figure out which glassware is going to be best for separating these compounds. And the answer is the separatory funnel, which is A. And what this does is you pour in the 2 solutions. So we have the water, so the aqueous layer, and the hexane. And then you open the stopcock and let out all the aqueous layer. And then you stop it once the aqueous layer reaches here, and you have just your hexane solution with the O organic compound in it. So A is the correct answer. Problem 8. Which substance may be treated with bleach, sodium hypochlorite, to render it less hazardous? So this is a very trivia-like question. And you kind of have to know the chemistry of hypochlorite. But let's first start with properties. So hypochlorite, OCl-, is a oxidizing agent in most cases. So oxidizing agent. And let's just look at sodium cyanide, for example, which is our option A. Cyanide is the Cn-, this toxic Cn-. And then when we oxidize it with hypochlorite, what we actually create is cyanate, which is this OCN-. And if you know a little trivia about water treatment, this process is actually used to clean up cyanide-contaminated water. They oxidize it to cyanate, and then after that, they further oxidize it to carbon dioxide and nitrogen gas. So if this process is used in a treatment for purifying water and cleaning it, making it less toxic, this is probably our answer. And if you know this trivia, this question is pretty easy. I'm gonna go with that for A, but let's consider the other options. So we have ammonia. And actually, when ammonia reacts with the hypochlorite, toxic chloramines are created. So we have this like NaCl2 or like NH2Cl, these types of compounds, and these chloramines are not safe. So B is incorrect. C, hydrochloric acid. You can imagine when we mix hydrochloric acid and the hypochlorite anion, the hypochlorite, the chlorine is in a +1 oxidation state, and in hydrochloric acid, it's in a -1 oxidation state. When you mix these two together, you end up getting a comproportionation reaction and getting chlorine gas, so in a 0 oxidation state for both chlorines. Chlorine gas is not safe, so that is incorrect. Then ozone. Ozone is actually a stronger oxidizing agent than hypochlorite. When you add it to hypochlorite, you create the chlorate anion. And chlorates are generally toxic as well, so not that. A is correct. Problem 9. Which indicator would be most suitable for a titration to determine the concentration of ammonia in a window cleaning solution using aqueous hydrochloric acid? So this type of titration is a acid-base titration. In this case, it's a strong acid, HCl, and weak base, ammonia. So strong acid, come on, pen, please, function. Okay. Weak base. Dude, this pen, man. All right. Weak base. And we have to figure out which indicator is best for this titration. So Ariachrome black tea, this is actually a complexometric indicator. Okay, come on, pen. Complexometric indicator. So this is when you're titrating to figure out the amount of metal ions in solution with like EDTA or something. If you actually look up this indicator, the endpoint is a pretty blue color. And it's not that common, but the first time I heard of it was at the USNCO study camp when we actually used it for titration. But not sure if it's like totally expected that you would know this, but you should be able to figure out the answer when you reach the other answer choices. Then B, ferroin. This is a redox indicator. It has two colors, I think red and blue, but not entirely sure, in its oxidized and reduced forms. So that's what this is for. Clearly, it's not going to help us in our acid-base titration. Now, methyl orange and phenolphthalein are both acid-base indicators, so these are probably going to be our option choices. So now let's consider what happens. In a strong acid and weak base titration, the pH of the equivalence point is going to be acidic. Some of you might know the saying like strong always wins, so the strong acid is going to win, so the equivalence point is going to be in the acidic part. But let's think about why. So we have HCl and NH3. And when you combine them, you can imagine that we have this NH4 plus ion and the Cl minus. So in the final solution, these are our two ions in solution. Chloride is the conjugate base of a strong acid, HCl. So clearly it's going to be a very, very, very weak base. Most people call it a negligible base. And then ammonium is the conjugate acid of a weak base. So it is a relatively stronger type of acid, and it will donate protons into solution. It's not a strong acid, but it's not a negligible acid either. So this ion is the reason why at the equivalence point, when all HCl and NH3 are used, the equivalence point is going to be acidic. Now we consider the color change range of methyl orange and phenolphthalein. I believe the pKa of methyl orange is around 3.5 and phenolphthalein is around 9. So clearly methyl orange, which changes at a pH around 3 to 4, is going to be more helpful for us because the equivalence point is in the acidic range. If we use phenolphthalein, we're going to see a color change long before we actually reach the equivalence point. So C is correct. Problem 10. A test tube contains 4 milliliters of a solution that is 0.1 molar in one or more of the following salts: silver nitrate, manganese nitrate, and aluminum nitrate. 1 ml of 6 molar hydrochloric acid is added to the test tube, which causes neither a color change nor formation of a precipitate. After subsequent addition of 1.5 mils aqueous sodium hydroxide and 0.5 mils of aqueous hydrogen peroxide and brief heating in a hot water bath, there is a dark precipitate in the test tube. What may be determined about the cations initially present? So this is a question of descriptive chemistry and what type of precipitates form. So we know in the first part of the reaction where we're adding HCl, we're adding both protons and chloride ions to the solution. And what we know is silver chloride is a very common precipitate. Precipitates out, this white precipitate. And if there was any silver in solution, we would expect a precipitate to form. But the reaction tells us that neither a color change nor formation of a precipitate occur when HCl is added. So we know silver plus must be absent from solution. So with that, we know that either B or D is the correct answer. Now, let's consider the second reaction. We're adding aqueous hydroxide, so basic conditions, and an oxidizing agent, hydrogen peroxide. Come on, please, pen, be nice. Okay. Our oxidizing agent. So, and also the precipitate is a dark precipitate. And if you know the common oxidation states for manganese, you may know that MnO2 is a common precipitate in basic solution. Now, the reason why we need the oxidizing agent is because manganese is a +4 oxidation state, like here, but when we added it, it's only +2. So we know that manganese must be present in the solution, so we can eliminate B, and D is our correct answer. Problem 11. Ethane and diborane do not adopt analogous molecular structures. Which experimental technique would be least useful in establishing this fact? So we need to know what each of these methods tells us about a compound. Infrared spectroscopy tells us about the functional groups, the functionality. Come on, pen. In a compound. Mass spectrometry tells us the mass of each molecule, so mass. NMR spectroscopy tells us about the chemical environments. And X-ray crystallography tells us the crystal structure. And the question is asking us which experimental technique would tell us the least about the molecular structure. So IR spectroscopy tells us the functionality. So if we can imagine that we find some type of spatial arrangement of atoms that gives a characteristic IR peak, we have some information about the structure. So A is probably not correct because we have some information. Mass spectrometry, telling us the molar mass of each individual molecule. We already know the individual masses of ethane and diborane, and we're not getting any new information about the structures. So clearly this is not very helpful. B is probably going to be our correct answer. C, NMR, telling us the chemical environments. So if we know the chemical environments of each of the atoms, we can figure out what's next to it in space and stuff. So this is going to help us with the structure, and that's incorrect. And D, telling us the crystal structure is obviously going to help us with figuring out what the molecular structure is. So D is incorrect, and B is our answer. Problem 12. The concentration of a solution of potassium permanganate is determined by titrating it into an Erlenmeyer flask with solid ferrous ammonium sulfate hexahydrate, dissolved in dilute sulfuric acid, which error would result in a measured concentration of permanganate that is lower than the actual concentration. So let's first understand what's going on. So we have a known mass of this ferrous ammonium salt, so that's in here. And then we have our burette with our permanganate in here, and we don't know the concentration. So what we're trying to do is figure out the concentration by figuring out how much volume we need. Oh, that's a very bad question mark. Let me try that again. How much volume we need to titrate into this known amount of moles. We know how many moles of this salt are in here based on the mass. This is kind of like, it's not called a reverse titration, but this is where we have the analyte actually in the burette and the titrant in the reaction flask. This is common when we're standardizing reagents. So, just to know and understand what's going on here. And we know that we calculate the concentration. We have concentration equals the amount of moles that have reacted divided by volume. And what we're measuring is actually this volume part, the volume of permanganate we needed to add. This is known based off the reaction stoichiometry and the amount of ferrous ammonium sulfate that are in there. So let's consider each of the options. A, the titration was begun before the ferrous ammonium sulfate had fully dissolved in the sulfuric acid. So if not all of the ferrous ammonium sulfate dissolved in the sulfuric acid, that means not all of it is available to react with the permanganate. As such, we're not going to need as much permanganate to react, and the volume is actually going to go down for this reaction. And if we look over here, if our denominator decreases, the concentration is actually going to increase. And the question is asking us for something that lowers the concentration that we measure, and that's the opposite of what's happening here. So A is wrong. B, the sides of the Erlenmeyer flask were periodically rinsed down with deionized water during the titration. If you imagine that we add water, we constantly pour water into this reaction vessel, we're not actually changing the amount of ferrous ammonium sulfate that is reacting with the permanganate. So we're not going to change the volume of permanganate that we add, and our concentration is not going to be affected, so we're not going to get this lower error. C, some of the iron 2 ions in the solid ferrous ammonium sulfate has been oxidized to iron 3 on storage. Now, if we imagine what permanganate does when we react it with ferrous ammonium sulfate, permanganate is a strong oxidizing agent. And what it's going to do is oxidize these iron atoms, these iron ions. And if you imagine that we already oxidized some of the iron 2 to iron 3, we're not going to need as much permanganate to oxidize the rest of the iron 2 because there's less iron 2 in the solution, in the sample. So the volume again is going to go down and our concentration is going to go up. This is the opposite of what a lower error is. So this is wrong. That leaves us with D as the correct answer. Let's consider why. The burette was rinsed with distilled water and then filled with permanganate solution while still wet. So in the burette, if we add water into here, right, we rinsed it with water and we didn't clean out all the water, we basically added water to our unknown solution. This is going to dilute the solution of permanganate, and we're going to need more volume of this dilute permanganate solution to fully react with our sample down here. So in this case, volume is actually going to increase, and the denominator of this formula for concentration is going to increase. So the concentration is going to decrease, and that's the error that we're looking for. So D is correct. Problem 13. A sample of pentane is in a rigid closed container at 50 degrees Celsius and 1 atmosphere, which best describes what happens when the container is heated. So if we're adding it at 50 C and 1 atmosphere, we're already adding the pentane past the boiling point. So we're actually adding pentane gas to the reaction vessel. So if we're saying liquid, we look at option A, liquid pentane vaporizes, it was already a vapor. So this is not the correct answer because there's no liquid to vaporize. B, the intermolecular forces between pentane molecules become stronger. If you imagine that when we heat up the container, the temperature is going to increase, right? So temperature increases. The molecules are going to be moving past each other much faster. And if they're moving past each other much faster, they can't interact with those intermolecular forces for as long of a time. So the attractions are actually going to go down if we increase the temperature. This is the opposite of what this statement is saying, where they're saying the forces get stronger. So this is wrong. C, the average kinetic energy of the pentane molecules increases the definition of an increase in temperature is an increase in the average kinetic energy of the molecules. So this is correct. Also, if you imagine that the molecules are moving faster, we know kinetic energy equals 1/2 mv squared. If this v term grows, that means the kinetic energy is also going to increase. And then the the density of the sample decreases. We know that density is equal to, so rho is the symbol for density, is equal to mass divided by volume. And we're also told that this is a rigid closed container. Rigid meaning it won't expand at all. So volume is a constant. And clearly the mass of stuff inside is also going to be a constant. So that means if m and v are constants, rho is also going to be a constant. So the density does not actually change. That's incorrect. Problem 14. Which compound has the highest normal boiling point? Now, what we want to consider are the intermolecular forces and compare them for these compounds. So the highest normal boiling point means that it has the strongest intermolecular forces because it takes a higher temperature to shake the molecules apart from each other because they're holding onto each other tighter. So the first thing we need to consider is hydrogen bonding, and all of them have a hydroxyl group, so they will all participate in hydrogen bonding. That's not going to be a consideration. And then we can consider London dispersion forces. just strictly off mass, but these are all isomers of each other, so they're going to have the same molecular mass. The final thing we can consider is structure. So when we have a straight chain like so in this propute, right? So this is N-butanol, this butanol molecule. What's going to happen is we have all of this surface area right here to interact with other molecules through London dispersion forces. Come on, pen, let's go. All right, through London dispersion forces. However, for something like D, where we have this tert-butyl group, the surface area is significantly smaller. As you can imagine, that it's also much harder for the molecules to come in closer together, and as such, the London dispersion forces are going to be weaker for a branched molecule like this tert-butyl group alcohol, this tert-butanol. So we're gonna say that the straight chain alcohol is going to have the strongest IMFs, and as such, the highest boiling point. Problem 15, a very similar problem. A mole of which gas has the smallest volume at 0 degrees Celsius and 1 atmosphere of pressure? So the difference in sizes of non-ideal gases is going to come down to intermolecular forces. And as you can imagine, if the intermolecular forces are stronger, then the volume is going to be smaller because the molecules hold onto each other more tightly. So let's consider the options. Helium is both a very small molecule, and it does not have any dipole-dipole interactions because it's monatomic, right? So the LDFs are going to be weak, and there's no dipole-dipole forces. This is going to be they have very weak IMFs. So this is probably not going to be the right answer. Carbon dioxide is a linear molecule, like so, and there's no net dipole of the molecule because if you imagine that there's a dipole like so on this side and a dipole like so, like here, these dipoles cancel out, so there's no net dipole on the molecule. There's no dipole-dipole interactions, so this is probably not right. SO2, you would think is pretty similar. However, the structure actually looks something like this. The presence of a lone pair makes the molecule non-linear. Let me actually draw that slightly better so you can see it. Come on, pen. So S looks more like this. Is clearly not linear. So we have this dipole. These don't cancel each other out because they're not facing in completely opposite directions. So we're going to have dipole-dipole interactions, and this is probably going to be our answer. And now when we consider xenon, xenon is another noble gas, and it's monatomic and not going to have any dipole-dipole interactions. This is wrong. C is correct. Problem 16. Two compounds, A and B, are both solids at 20 degrees Celsius. In separate experiments, 1 mole of each is heated and its temperature measured as a function of the amount of heat added. Which statement about the compounds is correct? So first, let's understand what's going on in this graph right here. So everything starts at the same temperature, and as the temperature is rising when we're adding heat, both compounds are initially solid in this region. Now here, in this flat line region, we have the solid, liquid, phase change or transition. This transition. All right, and then lastly we have this liquid that gets heated up after we pass this flat line, right? So let's consider each of the options now that we understand what's going on in the graph. So A, the molar heat capacity of solid A is greater than that of solid B. Let's remember what heat capacity is. Heat capacity, C, is equal to the amount of heat provided divided by the change in temperature for the sample. Now, if we look at heat capacity of solid A versus solid B, solid A changes more in temperature, right? It goes from 20 degrees to 60 degrees when, why is my pen bugging out, dude? When about 2,000 joules of heat are added, and compound B only goes from 20 to 40 degrees Celsius. So compound A has a larger value of delta T for the same value of Q, and as such, its heat capacity is actually going to be lower than that of solid B. So A is incorrect. Now let's think about the molar heat capacity of liquid A is greater than that of liquid B. This one is kind of unclear. If I had to guess, they were both equal because the slopes of these two lines right here are approximately the same, right? This is how much temperature changes with respect to heat, which is kind of what's going on right here. So the slopes are kind of about the same, so I would approximate the heat capacities to be the same, but I'm not entirely sure, so I'm not going to cross the answer out. I'm just going to leave it for now. Problem C, the melting point of A is less than that of B. So we said that this region right here is the solid liquid transition phase. That's also known as the melting point. So the temperature of the melting point for A is 60 degrees, and the temperature from the melting point of B is 40 degrees. So clearly the melting point of A is not less than that of B. C is incorrect. Lastly, the heat of fusion of A is less than that of B. Let me just kind of clean up my graph here a little bit. Okay. So the heat of fusion is going to be the amount of heat that it takes to go from the solid to liquid phase. And let's look at that for both of these options. For compound A, we started at 2,000 joules of heat added, and then we ended around 5,000 joules of heat added. So the heat of fusion is about 3,000 joules for this 1 mole sample. Now for compound B, let's say we also started around 2,000, but we clearly used more heat. We ended up around, let's say, 5,500 joules. So it requires more heat to convert the solid B to liquid B than it takes to convert solid A to liquid A. So we can say that the heat of fusion of A is less than that of B because it required less energy. So D is correct, and we don't even need to consider B. All right, problem 17. This is a harder problem if you don't have a physics background, but let's go through it anyway. A sample of a pure substance is placed in a sealed rigid container. So sealed and rigid container, and the pressure is measured as a function of temperature. Which is the best explanation for the results shown? So let's kind of understand what's happening first. At first, we have this kind of exponential looking, we don't know if it's exponential, but it's just a non-linear curve. And then right here at, let's say 60 degrees Celsius, the pressure shoots up dramatically. The slope of this line looks nearly like infinity, right? Because the line's basically vertical. So let's say, let's kind of understand what's going on here. So at first, let's think about what this can be. This clearly cannot be just a gas, because if it was just a gas, it would follow Gay-Lussac's law. If you're not familiar with that, I'm just going to use the ideal gas law because I think more people are familiar. So PV equals nRT. Let's just rearrange this. So P equals nR over V. So this times T. So if you can imagine, when we increase the temperature, it's going to have a linear increase on the pressure, right, by the scale factor. And clearly what we observe here is not a straight line. We don't have this straight line here. So this cannot be just a gas. Now, instead, what it can be is a liquid and its vapor, or a solid and its vapor. So the vapor pressure above the liquid or solid. And that is governed by the Clausius-Clapeyron equation, which is the natural log of P equals negative, I believe, delta H of vaporization or sublimation, depending on whether it's a solid or a liquid, divided by the gas law constant times 1 over T, plus C, which I think is delta S over R, but yeah, delta S over R. But yeah, and this is the type of graph that we might be expecting here, right? So if we did E to the both sides, we have pressure equals E to this value right here. And clearly that's not a linear graph. So that could explain what's going on here. But then how do we explain this very fast increase in the pressure? So the way I like to think about it is like this. At the start of the experiment, we have a box, a very small rigid container, and we have some liquid inside the container. As we heat up the liquid, right? So we increase the temperature. As we go up, what's going to happen is, and there's also the vapor pressure right here. So there's some vapor right here. What's going to happen is the liquid right here is actually going to expand a little bit. So liquids will expand by some thermal coefficient, and it's going to, let's say, take up this time 75% of the volume instead of just half. And there's still going to be this vapor here. And then as you imagine, as we keep heating it, the volume percentage of the liquid keeps going up and up. And then at some point, namely 60 degrees Celsius, what happens is the liquid actually occupies the volume of the entire container. So this whole container is liquid. And once the liquid is completely in the container, it's going to continue trying to expand as we add heat to it. But the thing is, liquids are much less compressible than gases. So it takes much more pressure to compress it to a volume that the liquid doesn't want to be in. Before 60 degrees Celsius, the container only has to compress this gas layer, this vapor phase layer. And we know that gases are more compressible. And liquids are nearly incompressible. So you can imagine that once we hit 60 degrees Celsius and the liquid takes up all of the volume, the container is going to have a much harder time withstanding the expansion of the liquid. So the pressure is going to shoot up immediately and very fast. And that's what's going on right here in this part of the graph. So let's just, now that we understand what's going on in this reaction vessel, let's look at the answer choices. Option A, at lower temperatures, the substance is a mixture of solid and vapor, while at 60 degrees, the solid melts to give a mixture of liquid and vapor. We know that there can't be vapor present in the final part of the graph at 60 degrees Celsius, because then it would still be relatively compressible and we wouldn't have this large shooting up going on right here. B, at lower temperatures, the substance is a mixture of liquid and vapor, while at 60 degrees Celsius, only liquid is present. That's exactly what we just mentioned. This matches our analysis and is the correct answer. C, at lower temperatures, the substance is a mixture of liquid and vapor, while at 60 degrees Celsius, only a supercritical fluid is present. Supercritical fluids are much more compressible than liquids, and we probably wouldn't see this, rapid shooting up. Again, that indicates incompressibility, so this is not correct. D, at lower temperatures, the substance consists of vapor only, while at 60 degrees Celsius, only a supercritical fluid is present. As we said before, because we don't observe a linear relationship between pressure and temperature, it cannot only be vapor initially, so this is wrong. B is correct. All right, problem 18. Cesium chloride crystallizes in a primitive cubic unit cell, with each cesium ion surrounded by 8 chloride ions arranged in a cube. The density of the solid is 3.988 grams per centimeter cubed. What is the cesium chloride distance? So let's solve this problem. So let's just draw out what it looks like. I'm not a great drawer, so bear with me, but let's see. So let's draw this cube. Come on, please, pen, cooperate. Right, and then it goes like this. So this is our cube, and we're told that the chloride ions are at each of the corners. So let's just imagine, I'm not going to draw the chloride ions because it's going to get really clustered, but at each corner there's going to be a chloride. Come on, pen. There's going to be a chloride, and then at the very center of the cube, let's just draw a circle here. This is going to be a cesium plus ion. Now, let's figure out how many formula units of the CSCl are in one cube. So since there's only one cesium in the center, we would imagine that there's only one formula unit, but let's figure out how much chloride's in the unit. So at the corners here, we have this sphere of chloride, and each of these chlorides is shared by 8 other unit cells, if you can visualize the 3D structure. So that means each of these corner chlorides contributes 1/8 of a chloride to each cell. And in this one cell, we have 8 chloride ions. If we imagine there's 8 corners of a cube, so therefore there's 1 total chloride ion if we add up all those 1/8. So we have 1 unit of CSCl. All right. So now what they're asking us to find is the CSCl distance. So the way we're going to do that is by working out the dimensions of the cube. To do that, let's use the density. We have 3.988 grams of, so rho, which is our density, as I mentioned before, 3.988 grams per centimeter cubed. And we know that cesium chloride, they gave us the molar mass, is 168.4. Come on, pen, dude. Grams per mole. But the thing is, in 1 unit cell, we don't have a mole of these. That would give us 168.4 grams. We only have 1 of these units, so we need to divide by Avogadro's number. So that's Na. And that's going to come out to, I believe, let me look at my notes. All right. I did not do it. All right, so let me just plug in my calculator. 168.4 divided by 6.022, 6.022 times 10 to the 23rd. And that's going to give us 2.80 times 10 to the minus 22 grams per unit cell in 1 unit cell. And let's calculate the volume of 1 unit cell now, because we have the amount of mass and the density. So we can say 3.988 grams per centimeter cubed equals this mass, 2.8 times 10 to the minus 22, divided by some volume, which we don't know. And if we solve for that, let me plug in my calculator. So we're gonna divide by 3.988. That's gonna give us a volume of 7.01 centimeters cubed. Nope, times 10 to the minus 23rd. Times 10 to the minus 23rd. So for 1 unit cell. And then we can calculate the edge length of the unit cell, because the edge length of a cube is just gonna be the cube root of the volume. So we take the cube root of this number. So let me just do that. And the edge length is 4.12 times 10 to the minus 10. Sorry, 10 to the minus 8. This pen will not function. 10 to the minus 8 centimeters. And if you know how to convert to picometers, that's going to be 412. Please, pen, cooperate. 412 picometers. And so that's our edge length of the cube, right? So that's this. So this is 412 picometers. Now, what they're asking us is to figure out what the CS-Cl bond length is. And then you can imagine that that's going to be the distance between the corner and one of the corners and the center of the molecule. So the way we can find that is by figuring out the diagonal that goes through the center of the cube, like so. And if you know geometry, we know that the diagonal through the cube is equal to the square root of 3 times the edge length. So diag, let's call that D. Oh, come on, pen. Okay. Diagonal D equals the square root of 3 times 412 pm, 714 picometers. And then the CS-Cl distance is going to be half of the diagonal. So we're going to divide that by 2, and that gives us 357 picometers. I don't know why my pen's bugging today. All right, and that's C, our correct answer. Problem 19. Steam turbines convert heat into mechanical work. Which statement best describes the efficiency of this process? So let's think about this. A, 100% because energy is conserved. In no real engine, no real engine will ever achieve 100% efficiency, because the second law of thermodynamics tells us that heat spreads out over time. So we cannot build a system which contains all of the heat from a reaction. It will gradually seep out. As such, we cannot have an 100% efficiency engine. So A is incorrect. B, less than 100% because the steam decreases in temperature. Sounds good to me. C, greater than 100% because the turbine increases in kinetic energy. No engine can be greater than 100% efficient because that means it would have to create more energy than is put into it. And that violates the first law of thermodynamics, which is that energy cannot be created or destroyed. That is incorrect. D, can be greater than, less than, or equal to 100%. This is not right because it says can be greater than. That's not true. And it cannot be equal than either, as we just discussed. So this is wrong. B is correct. Problem 20. At what temperature is the decomposition of tungstic acid, H2WO4, solid, to tungsten trioxide and water vapor spontaneous under standard conditions? If we imagine that this reaction is not spontaneous and then becomes spontaneous at some temperature, it will go from positive delta G to negative delta G, and the point where it just becomes negative is where delta G equals 0. So what we're going to try to find is where delta G equals 0. Delta G naught equals 0. And the way we do that is by calculating delta H naught and delta S naught. And delta H naught and delta S naught can be calculated by the products minus reactants formula. So let's do that for delta H. If we use the values in the table, the products of the reaction are WO3 and H2O gas, and the enthalpies are negative 840 and negative 240. So we're going to add, so equals negative 840. So the products plus negative 240. And then we're going to subtract the reactants, which is this tungstic acid, which is negative 1130. And that's going to give us a delta H value of 50 kilojoules per mole, positive 50 kilojoules per mole. All right, now for delta S, we're going to use the same products minus reactants formula. And that's going to be products, which is these two, 80 and 190. So 80 plus 190 plus 190. And we're going to subtract our reactants, which is 140. So here, minus 140. Dude, this pen sucks. All right, and this is going to equal 130 joules per mole Kelvin. And now that we have the values of delta H and delta S, we can use our formula for delta G, which is delta G naught equals delta H naught minus T delta S naught. And I'll remind you that we're trying to find when delta G naught equals to 0. So 0 equals 50 kilojoules, we're working in kilojoules, minus some temperature. And because we're working in kilojoules, I'm going to need to divide this value in joules by 1,000. So T times 0.130, right? And when we solve for T, T comes out to 385 Kelvin. So we're going to know that C and D are wrong. Now, let's think about, is the reaction spontaneous when T is greater than 385 or less than 385? If we look at our formula for delta G equals delta H naught minus T delta S, a reaction is spontaneous when delta G naught is negative. So we know that delta S naught is positive, so that means this T delta S naught is going to be negative. This negative T delta S naught is going to give us a negative value. And if you imagine that we increase this value of T, delta G naught is going to become more negative because we're adding a larger negative T delta S term. So we would imagine that at temperatures higher than 385, the reaction will be spontaneous. And that matches with A. A is correct. Problem 21. In a well-insulated container, 10 grams of solid octane at its freezing point is added to 300 mils of liquid octane at 0 degrees Celsius. After the equilibrium is reached, the temperature is negative 6.3 degrees Celsius. When the experiment is repeated under the same conditions except with 100 grams of solid octane, what is the final temperature? So we're going to use our Q equals MCAT formula. I'll write that out. Q equals MC delta T. And we know the heat lost by, or the heat gained by the solid is going to equal the heat lost by the liquid, right? Liquid octane. But we need to put a negative sign because of the sign convention. One's losing and one's getting heat, so we're going to put a negative here. Right? Then we can plug into our Q equals MCAT. So for the solid is going to have some mass, right, times the heat capacity of the liquid octane, because the solid will become a liquid, times the change in temperature. But it's going to take energy to change the solid to a liquid. So that's going to be plus the mass times delta H. So the delta H of melting the compound. And that's going to equal the negative of the mass of the liquid times the heat capacity of the liquid times the change in temperature of the liquid. Now, if you're used to delta H of melting or fusion, which is this value right here, which is what this is, usually it's reported in kilojoules per mole. In this case, it's actually going to be joules per gram because that's the units that works out with this equation, but that's not really relevant because it doesn't affect our calculations at all in this case. Now, let's plug in for these two experiments. For experiment 1, we have 10 grams of solid octane. So we have 10 grams. I'm not going to use units so that we don't, it doesn't get too messy. So we have 10 grams times our heat capacity C and our delta T. So what's our change in temperature? We initially started at negative 56.9 degrees Celsius and we ended at negative 6.3 degrees Celsius. So let's just figure out what that is. Negative 6.3 plus 56.9. That's going to be a change of positive 50.6 degrees Celsius. Oh, I said I was not going to use units, and I proceed to use units. Let me not do that. 50.6 degrees Celsius, and then plus the 10 grams times that delta H in terms of joules per gram. And that's going to equal negative of whatever the mass of liquid octane we're adding is. So let's figure that out actually. Liquid octane, we're adding 300 mils, and then times 0.71 grams per mil. And that's going to come out to 213 grams. So this is minus 213 grams times our heat capacity C times delta T, which goes from 0 to negative 6.3. So this is times negative 6.3 degrees. Nope, we're not using units. Negative 6.3. All right, sorry about the bad handwriting and running out of space. I'm not really used to using, well, this is my first time actually using the pen, and clearly I'm struggling a little bit, but I'll keep going. Now, for experiment 2, we have a very similar equation. We have our, this time, 100 grams of solid octane. So 100 grams times the heat capacity C, and then times the change in temperature, which this time we don't know because we don't know what the final temperature is. That's exactly what we're solving for. So it's going to be final temperature minus initial, which is, what was it, 56.9? Yes. So minus 56.9, minus negative 56.9 is equal to adding 56.9. So plus 56.9. Right? And that's going to plus 100 times delta H, and that is going to equal again negative times 213 times the heat capacity, and this time this equation where we had negative 6.3, again we're not going to know what the final temperature is. It's going to be temperature final minus initial, which is 0, so it's just going to be temperature final. So your algebra skills might be telling you that this is not possible because we have 3 variables. We have C, we have delta H, and we have temperature final. Yet we only have 2 equations. But the thing is, let's just try this out and see what happens. So for experiment 1, we only have C and delta H in our equation. I'm going to leave the algebra to you, but when we do the algebra and figure out what delta H is in terms of C, we get delta H is equal to 83.6 times the heat capacity C, right? The specific heat capacity. Then we can plug this value of delta H into our equation. So we have 100 C times TF plus 56.9 plus 100 times 83.6 C equals negative 213 C times temperature final. Now, if I do the algebra and bring everything over to one side and expand out all of these values, what we're going to come out with is, I wrote it down already. Let me see. What we're going to get is 313. Okay, come on, pen. 313C times TF is equal, plus 14050. C is equal to 0. And again, as we expected, we can't fully solve this because we have still 2 variables and only 1 equation. Now, what we can do is divide both sides by C, because C we know cannot be equal to 0, right? So we're not really getting rid of any information if we're dividing by C. So that gives us 313 times TF plus 14050 equals 0. And if we move the 14050 to the other side and divide, we find that T final is equal to negative 44.9 degrees Celsius. So, amazingly, we can figure out what the final temperature is without knowing anything about the heat capacity or the delta H fusion. We only know their relationship, but we don't know their absolute values. So, but we can still find the solution, which is going to be B. Problem 22. Amphiphilic species like this carbonate can aggregate into micelles in water as depicted schematically below. Delta S for micelle formation is positive, which best explains why. So what we have is all of these amphiphilic carboxylates, like these right here. They come together and form this structure, this micelle. And what they're telling us is delta S for this process is actually positive. And this might surprise you because we have all these free-looking amphiphilic species, and they all come together to a tight clump when we expect delta S to be negative. So let's look at the explanations and see if we can figure out why. A, amphiphilic compounds are solvated by an ordered layer of water molecules. So if these amphiphilic compounds are initially solvated by water molecules, we imagine that each one has these clusters of waters around it. They're originally in these like cage-like water molecule structures. And then as we create the micelle, we actually break all these cages and all these free water molecules are released. So this breaking of these like solvated cages, releasing water molecules, can be a source of our positive entropy that's contrary to what we expected. So therefore A is a possibility. So I'm going to leave it like that. B, micelle formation involves converting many independent amphiphilic compounds into a single larger micelle. As we just said, this would contribute to a negative delta S, and that's kind of what we expected, but that's not observed. So this is not the correct answer. C, water molecules are trapped in the hydrophobic interior of micelles. If we imagine trapping water molecules in the interior of the micelles, that means we're restricting their movement, and therefore they can have less microstates and positions. So therefore, C would give a negative delta S, and that's not what we're looking for. So that's wrong. D, water molecules form ordered structures around the exterior of micelles. If we created more water cages around the micelles, that would again decrease delta S because those water molecules have restricted movement and less microstates, so that's wrong. A is correct. Now, this is actually more common than you might think in other applications. Kind of in the reverse is the autoprotolysis of water. So we have water, and it goes to H plus and OH minus. Some of you might want to use the H3O plus and two waters, but it doesn't really matter. And when I first saw this problem in USNCO 2015, part 2, we were calculating thermodynamic values or something. I think it was 2015, I'm not entirely sure. Delta S actually came out to be a negative number. I have no idea what it was. Some negative number. And I was initially surprised. I was like, oh, did I do my calculations wrong or something? Because we're creating two species out of one initial clump. But the thing is, when I looked up the explanation why, it's because these ions are heavily solvated by water molecules. So if you can imagine the H3O plus, right, there's going to be water molecules everywhere surrounding these ions to solvate them, right, and stabilize them. And what this means is the cost of creating these ions is actually ordering like a large cages around the ions, and this overall decreases the entropy, even though we're creating two units out of one species. So, you know, this is kind of like the reverse of what's going on here. We're starting with the caged up, not ions, or yeah, they are ions in this case, and then we're creating a larger structure, but in the process, we're releasing these water cages and releasing stuff. So the delta S of what would be the reverse reaction of this is actually positive. And yeah, I thought that was a cool connection. Sorry for interjecting with that, but anyway. Problem 23, what is the changing Gibbs-free energy of formation for ethene at 25 degrees Celsius? We're going to use delta G naught equals delta H naught minus T delta S, just like we did before. And we're going to calculate delta H naught and delta S naught the same way we did before, which is product minus reactants. But first, actually, let's write out the equation for what's going on. So we are forming ethene from its most stable, elements. So that would be carbon in its graphite form. Graphite. And dude, this pen is so bad. Plus hydrogen, gaseous, and we're creating our ethene. Come on, C2H4 gas. And to balance the reaction, we're going to need 2 graphites and 2 hydrogens, 2 hydrogen gases. So now let's just do our products minus reactants. So delta H naught is going to be the reaction enthalpy of the products, which is 52.4, minus the reactants, which is going to be 2 times 0 and 2 times 0. So that's going to be just 0. So delta H naught is going to be positive 52.4 kJ per mole. And then delta S naught, we're going to also use this products minus reactions. And this time the product is this 219.3. And then the reactants are 2 graphites, so 2 times 5.7. Plus 2 hydrogens, right? 2 hydrogens, plus 130.7 times 130.7. And this equals, I already did it in my notes, so why am I in my calculator again? Negative 53.5 joules per mole Kelvin. Joules. So when we do delta G naught, we're going to do it in kilojoules. So we're going to do delta G naught equals delta H naught minus T delta S. So that's 52. Come on, pen. 52.4 minus T, which in this case, in the problem, they tell us 25 Celsius, which is 298 Kelvin, 298 delta S. And again, we're working in kilojoules, so we're going to have to divide this value by 1,000. So that's negative 0.0535. And this comes out to a value of positive 68.3 kilojoules per mole. Positive 68.3, sorry. I'm really struggling with this pen today. And that's D. Problem 24. The heat of formation of methane is negative 74.6 kilojoules per mole, and the bond dissociation enthalpies of several bonds are given in the table. Based on the data, what is the molar enthalpy of sublimation of carbon graphite to form carbon gases? So let's imagine what these bond enthalpies can tell us. We know that we can calculate the heat of a reaction using bond enthalpies. So let's write out what that reaction might be in this case. In this case, we have carbon gaseous, right? Plus 2 hydrogen gases. And that goes to methane. So to calculate the reaction enthalpy of this reaction, we're going to use the bonds broken minus bonds formed equation. So we have delta H equals sigma bonds broken minus formed. And in this case, we are going to be breaking, as you can imagine, the carbon's already free, so we're not breaking any bonds. And then we're breaking 2 hydrogen gas molecules. So that's going to be breaking 2 HH bonds. And then we're going to subtract what we're forming. We're forming 4 CH bonds, right? If we look at the structure of methane, it's like this, CH, H. So there's 4 CH bonds. So we're going to subtract 4 CH. So we're just going to plug in our values. So delta H naught is going to equal 2 times the hydrogen bond association, which is 432. And then minus 4 times the carbon hydrogen, which is 413. And this comes out to negative 788 kilojoules per mole. Right. We're also given more information in this question, which is the heat of formation for methane. And we know that the heat of formation is defined by the compound forming from its elements in their most stable state. And for carbon, that's actually graphite. So that's going to be carbon graphite, right? Plus our hydrogen gas. We're going to need two of these. And that's going to yield our CH4 gas, right? Our lovely CH4. And then we're given that delta H naught for this reaction is -70, I believe 4. Let me check. Yes, -74.6 kilojoules per mole. When you think about it, this reaction and this reaction up here are very, very similar, right? But this one releases so much more energy. The reaction 1 releases 788 kilojoules per mole, and reaction 2 only releases 74.6 kilojoules per mole. Why is there such a big difference? Let's draw an energy diagram. So, increasing energy going upwards. We have the reaction 1 reactants, and the reaction 2 reactants. And the product are all going to be the same energy because both reactions produce the same product. Reaction 2 releases less energy, and while reaction 1 releases significantly more energy during the reaction. This is because there's a huge energy gap between the reactants of reaction 2 and reaction 1. Reaction 1 is much higher in energy, and let's think about why that is. So if we look at the reactants, the hydrogen is the same, and the hydrogen is the same here. So the only thing that's remaining is this carbon gaseous versus carbon graphite. And the difference in energy, which is this gap right here, is caused by the difference in energy between these two. And the difference in energy between these two is actually the heat of sublimation of graphite. If we imagine how much energy it takes to bring the graphite to the gaseous state, well, that's going to be our heat of sublimation, and that's exactly what this problem is asking for. What is the molar enthalpy of sublimation? So let's figure out what the difference between these two energies are, which is going to be the difference between the reactions. So that's just going to be -74.6 kilojoules per mole. And we're going to subtract our -788 kilojoules per mole. And that comes out to positive 713. All right. And that is A. That's correct. 25. For a reaction X plus Y yields Z, data for 3 experiments are given. And here, which mechanism is consistent with the above data? Reactions shown are reversible and assumed to be rapid and unfavorable. So let's first figure out the order with respect to the concentration of each reactant. So if we imagine from this trial, let's call this row 1 to 2. So from 1 to 2, the concentration of X increases, so it triples, so concentration of X. And what happens is the rate also triples, so rate increases by 3. And then, what this tells us about the reaction order with respect to X is that it's first order, right? Because 3X change in X gives a 3X change in the rate. So this is first order with concentration of X. And then from experiment 2 to experiment 3, X does not change. Y does change. It triples, so Y triples. And then the rate actually increases by 9. So rate increases by 9. And because the rate increases by 9, and 9 is 3 squared, we can say that the reaction is second order with respect to Y, the concentration. So second order. So with respect to the concentration of Y. So we're going to need to look for some mechanism with these properties. So for the first step, X plus Y yields Z. This is, there's only one step, so that's going to be the rate determining step. And that predicts a first order in X and first order in Y. So this is clearly not correct because that doesn't match the first and second order that we expect. So first order in X and second order in Y. So that's not right. Now for B, we have this mechanism. And we're told that reactions shown as reversible are assumed to be rapid and unfavorable. If they're rapid, that means the second step is going to be the rate determining step is the slower one. So we're going to say the rate equals K times the concentration of X2 times the concentration of Y. And X2 is an intermediate, so we need to figure out an expression in terms of the other reactants. Because we know that the equilibrium reaction is faster, we can say that the reaction reaches equilibrium before the second step starts to proceed. So we can say the equilibrium constant K equals concentration of X2 over the concentration of X squared, right? This is just the law of mass action for this equation right here. And then we can solve for the concentration of X2 in terms of X squared. So concentration of X2 equals K times the concentration of X squared. Hopefully so far so good. And now we can substitute this expression for X2 into here. So we have the rate equals K times X squared times Y. So this gives us reaction that's second order in X and first order in Y. And that's not what we're expecting. We want first order in X and second order in Y. So B is not correct. Now, looking at mechanism C, we see that this is actually the same exact mechanism as Y, except the identities are switched. So the Y goes first, you can form Y2, and that reacts with X. So we would expect this to form the flip-flop of like reaction order, and this would probably give us rate equals K times Y squared times the concentration of X. So if we did the same exact derivation, we would find this. And this actually matches our experimental data because it's second order in Y and first order in X. I'm not going to take the time to derive for D, but it's a very similar process. You can try it as your own exercise. I'm going to continue moving on because we spent a lot of time on that problem. All right, problem 26. Polonium-208 undergoes alpha decay to form stable lead-204 with a half-life of 2.9 years. A sample of polonium-208 was measured with a Geiger counter 5.2 years ago as having an activity of 1320 disintegrations per second. What is its activity today? So we know activity will have with every half-life. So we can just figure out what the activity will be 5.2 years after it was 1320 using our half-life formula. So it's going to be whatever our activity, let's call that A, equals our 1320 times 1/2 to the, how many years? 5.2 years ago, 5.2, divided by our half-life, which is 2.9. And that gives us our answer of 381 disintegrations per second. So seconds to the -1, and that is our answer. If you're a little bit confused about how this comes about, let me kind of explain the formula, because most, I guess, chemistry is taught where we use the integrated rate law for the first order reaction as such. So we use natural log over 2 for rate constant or whatever. We don't really need that. Let me explain what's going on. So we can say the activity at any point after the initial time is going to be whatever the initial activity was. So let's say this is a initial, and then times 1/2 to the amount of time that's passed in years divided by the half-life, so t 1/2. Now, why does this formula work? So what happens is we start with some initial concentration, and t will initially be 0. When t is 0, this whole entire exponent, this is an exponent, will be equal to 0, and half raised to the 0 is 1, so this a initial is going to be a, right? So initially, the activity is going to be a initial. Then, after 1 half-life, so t equals t 1/2, right? After 1 half-life, we plug in t 1/2 up here in the exponent, right? We're going to have t 1/2 over t 1/2, that's equal to 1. So 1/2 to the power of 1. We have a initial times 1/2 to the power of 1. That's just going to be a initial divided by 2. And so we expect activity will half after a half-life, and et cetera, et cetera. So if we plug in any time to this t up here, we can figure out how much is remaining after that much time. So I just plugged in the 5.2 years and the half-life of 2.9 and the initial activity of 1320. That's how I found the answer. Might have over-explained it a little bit, but oh well. 27. A reversible reaction occurs as follows. 2A plus B yields, or is in equilibrium with C and D. Under a certain set of conditions, the rate law for the forward reaction is determined to be rate equals Kf times A times B. What is the rate law for the reverse reaction? So let's first start with the equilibrium constant K. And if you know, the equilibrium constant K is equal to the rate of the forward reaction, rate constant of the forward reaction divided by the rate constant of the reverse reaction. So that's equal to Kf Kr. We also know that the equilibrium constant using the law of max action, in this case, is going to be, if we use Kc, that's going to be concentration C, concentration, come on pen, please cooperate, over concentration of A squared times B, right? So we can set these two equal to each other. So we have Kf Kr equals concentration of C times concentration of D over A squared plus B, or A squared times B. Now, we're told that the forward reaction is Kf times A times B. So let's solve for Kf on one side. So what I'm going to do is multiply both sides by Kr and AB. So that's going to give us Kf times AB. This is algebraic manipulation. Times AB is going to be equal to Kr times C times D divided by A. And we know that this is an equilibrium reaction, and when reactions are in equilibrium, the rate of the forward, which is given to us right here, this is the rate of the forward reaction, is going to equal the rate of the reverse reaction. So then we know that this is actually the rate law for the reverse reaction. And then that matches with B. Problem 28. A compound A reacts by two independent irreversible pathways to give two products B and C. At 300 Kelvin, 35% of the product is B, while at 320 Kelvin, 70% of the product is B. What may be concluded about the activation energy of the pathway to form B compared to the activation energy of the pathway to form C? So we know that at 300 Kelvin, the ratio of the rate constant to form B over the rate constant to form C is going to be 35 over 65. Because if we imagine that 35% of the product forms B and 65% of the product forms C, this is like, you know, a race to figure out like whether the product or A becomes B or C, and the relative values of the rate constants will tell you like the relative proportions of how much of B and C form. So then at 320 Kelvin, we have Kb over Kc by the same logic is going to equal 70 over 30. All right. Now that we have this, I'm going to arbitrarily decide that the actual value of Kb is 35 at 300 Kelvin, and the actual value of Kc at 300 Kelvin is 65. However, we don't actually know the values of Kb and Kc at 320 Kelvin. So I'm just going to say let x equals Kb and y equals Kc at 320 Kelvin. Now let's set up the Arrhenius equations for each of these reactions. So for reaction B, the natural log of x over 35 equals negative EA of B over R times 1 over 320 minus 1 over 300. And then for reaction C, we have natural log of y over 65 equals negative EA C over R times 1 over 320 minus 1 over 300. Now what I'm going to do is subtract these two reactions from each other, so that way we can try to find a relationship between EAB and EAC, which is what this question is asking. So we're going to have natural log of x over 35 minus natural log of y over 65. And that's going to equal negative EAB plus EAC. I'm just going to do some algebra here. And then times 1 over R times 1 over 320 minus 1 over 300. So I just factored out like this bunch right here from these two. If you do the subtraction, you can see, like in one step, you'll see what I'm talking about. And then I'm going to use my log rules right here to figure out the natural log of 65x over 35y. So we know when we subtract two logarithms, we can divide our arguments, and that's what we have here. And that equals negative EAB plus EAC times 1 over r times 1 over 320 minus 1 over 300. Right? Now, it seems like we're kind of at a dead end, because now what, right? But we also know that the value of this fraction, x over y, is actually equal to 7/3, because we have here, what we have here, right? X is kb and y is kc, and we know that ratio is 70/30, so this is 7/3. So we can plug that into our equation. So we have natural log of 65 times 7 divided by 35 times 3 equals negative EAB plus EAC, and then 1 over r, 1 over 320 minus 1 over 300, and then r is a constant. So when we solve for EAB and EAC, we actually find that EAB is equal to EAC plus, sorry, look at the thing, plus I think 58.5 degrees, 58.5 kilojoules per mole, something like that, 58.5 kilojoules per mole. And if we look back at our options, this means that the pathway to form the activation energy for the pathway to form B is 59 kilojoules per mole higher than that of C. So B is our correct answer. Problem 29. The irreversible reaction A plus B yields C takes place by the following two-step mechanism involving an intermediate X whose concentration is low throughout the reaction. What statement cannot be correct regardless of the values of K1, K minus 1, and K2? So there's two cases here. We don't know the rate constants, so we don't know which step is rate determining. So case 1 is the first step is rate determining, and case 2 is the second step is rate determining. So in case 1, if the first step is rate determining, clearly the reaction is first order in A and 0th order in B, because B is not involved in the reaction until after the rate determining step, and A is only involved once in the rate determining step. So this would be first in A, 0th in B. Now case 2 is a little more interesting. Case 2 is where the second reaction is the rate determining step. If we imagine that this reaction is the rate determining step, and the first reaction is significantly faster, we can apply the pre-equilibrium approximation, which says that A and X reach equilibrium before this X plus B reaction even happens. So we can use the equilibrium constant K is equal to the concentration of X divided by the concentration of A. We also know that the rate law is going to be rate of like this, so rate equals K2 times X times B. So from here we can solve that X equals the rate constant, the equilibrium constant K times A, and then we can plug this value for X into here, so we can say rate equals K2 times K times A times B. So this case would be first in A and first in B. So what we can tell is the reaction order in B can either be first or 0th, but the reaction order in A is always first. It's first here and first here. So therefore the reaction can never be 0th in A, so this is correct. All right, last problem for this section. Problem 30. Nitramide decomposes to nitrous oxide in aqueous solution via this reaction. In solutions with pH greater than or equal to 12, the rate law for this reaction is the following. The reaction is monitored with pH equals 12.0 and pH equals 12.3, which graph best represents the time dependence of the nitramide concentrations in two experiments. So let's first think about what's going on here. As we can see up here in this reaction, H3O plus is never used or consumed. So what we can say is the concentration of H3O plus is constant, right? So now we have our rate law here, where rate equals K times this nitramide concentration times this, or divided by H3O plus. And what we can rewrite that as is rate equals K prime times NH2 NO2, where K prime equals the original rate constant K divided by the concentration of H3O plus, right? In essence, I just factored out like this term and turned it, this term, and turned it into K prime. And we know H3O plus is constant, and so this must be a constant. And what we would expect is that the reaction is going to follow first order kinetics with respect to nitramide. And first order kinetics, just like radioactive decay, for example, is going to give us an exponential decay graph. So clearly A and B are already incorrect. Now we need to determine between C and D. So let's consider what's going on. At pH equals 12 versus pH equals 12.3. At pH equals 12 and pH equals 12.3, at pH equals 12.3, this is going to be more basic. And what does more basic means? It means the concentration of H3O plus is lower, right? We're going to lower the concentration of H3O plus. And if the concentration of H3O plus is lower, we can imagine that our pseudo rate constant K prime is actually going to be higher because H3O plus is in the denominator, and if we decrease the denominator, K prime is going to go up. And if K prime is higher, that means the reaction is going to be faster at pH equals 12.3 compared to pH equals 12.0. Now, if we look at our options, in C, the curve for 12.3 is always higher than the curve for 12.0. And this is kind of the opposite of what we're expecting, because at any point, the nitramide concentration is higher at 12.3, at pH equals 12.3 versus 12.0, and that's not what we want, because we would expect the concentration of nitramide to be lower as more of it has decayed, and the reaction was faster. D, on the other hand, has the curve for 12.3 lower because more of it has decayed in a shorter amount of time. And this kind of follows our analysis. So D is correct. And that just wraps up our session for the first half of the USNCO Part 1 national exam. I hope you found this informative. Please leave your feedback in the comments, and I will try to respond to any questions if you have any. This is my first time doing any video like this, and clearly my first time ever using this pen, but I hope you found it helpful. Thank you for watching.